Okay, so in this problem we have a thin, homogeneous bar, which has mass m and length L, and we're told that the bar is released from rest to the position where the theta is a given value. And we're also asked to assume that all surfaces are smooth. And based on this, we want to find the angular acceleration of the bar upon release. Okay, so since we're looking for an angular acceleration, that's a big red flag to us. We want to solve this problem using Newton's second law, and for that we're going to need a free body diagram. And so in this regard, we can note that we'll have the weight of the bar, of course, at the center of mass. And because the surfaces are smooth, we'll simply have normal forces at each end. So we'll have this as NA, and this is going to be NB respectively. And I'll sketch in the angle theta here simply for reference. And we know upon release, this thing can have an acceleration mag in the x, it can have an acceleration component mag in the y, and it can have a rotation component which I'll call I about g times alpha. So now that I have my free body diagram in hand, I can move on to my second step, which is to write down my kinetics equations. And so if I'll start by saying the sum of forces in the x has to equal m times ag in the x, and that's going to give me minus nb is equal to m times ag in the x. Let's call that equation 1. I can also sum forces in the y direction here and set that equal to m times ag in the y. And if I do that, I'll have here na minus mg is equal to m times ag in the y, and we can call that equation 2. In addition, I can sum moments in this case about point G, and I'll do so in a counterclockwise positive sense and set that equal to I about g times alpha. And if I work this one out here, I'm going to have a positive moment contributed by NB, and its moment arm, if I note again that this angle here is theta, is going to be given by L over 2 times the sine of the angle theta. And I'll have a negative contribution from NA, and its moment arm will be given by L over 2 times the cosine of the angle theta. And that's going to equal I about g, which is 1/12 ml squared, times alpha. And we can call that equation 3. Now if we look at our equations 1, 2, and 3 here, we'll realize we have 1, 2, 3, 4, and 5 unknowns. So we're going to need some equations here to help us out. And where we're going to get those equations is from, you guessed it, kinematics. So what I'm going to do is I'm going to start by relating 2 points where I have some information. And in this case, I'm actually going to relate 2 points that at first may not seem useful, but will turn out to be useful for us. So I'm actually going to write the acceleration of B is equal to the acceleration of A plus the angular acceleration of the bar across r of B with respect to A minus omega squared times r of B with respect to A. Now why I'm doing this is because I know that I'm not going to get enough information immediately by relating G in one of the endpoints. I'm going to need a little more than that. So if I look at this, we know that bar is released from rest, so the last term here is going to go to 0. And what do I have for information here? Well, I know AB is going to end up being purely in the J direction, or minus J as the case may have it. A is going to be purely in the I direction, or the minus I as the case may have it. And of course I'm using conventional XY axes here. Alpha will be some rotation in the K, and then R of B with respect to A is going to be L times the cosine of the angle theta in the I, plus L times the sine of the angle theta in the J. If I go ahead and work out the cross products here, what am I going to have? Well, I'm going to have AB in the J is going to equal AA in the I. K cross I is J, so I'll have plus alpha L times the cosine of the angle theta in the J. K cross J is minus I, so I'll have minus alpha L times the sine of the angle theta in the I. If I pull off the I component here, I'll have 0 is equal to AA minus alpha L times the sine of the angle theta. We can call that equation 4. And if I look at the J direction, I'll have that AB is equal to alpha L times the cosine of the angle theta. We can call that equation 5. Now you might say we didn't get a whole lot closer there. That you're right. It may appear like that at first, but indeed we did. And why did we do that? Well, we're going to use this fact right here, this one I just underlined, to help us out. In particular, what I'm now going to say is I want to find the acceleration of G with respect to B. And so if I do that, I know acceleration G with respect to B will equal, or I should say plus, alpha across R of B, G with respect to B, minus omega squared RG with respect to B. Again, noting we're released from rest, the last term here is going to go to 0, and so now I can substitute in. So now I'm going to have AGX in the I plus AGY in the J is going to equal AB, which we've already found to be purely in the J, plus alpha cross R of G with respect to B. I need to substitute in here, so we have alpha in the K. R of G with respect to B is going to be, let's look at where G is. G is going to be at our center of mass. B is on our top wall up there. So G with respect to B, let me just sketch this out. Here's L over 2. This is the angle theta. Here's B and here's G. So we need to go minus L over 2 times the cosine of the angle theta in the I, and we need to go minus L over 2 times the sine of the angle theta in the J. So if we go ahead and work out the cross products here on the right hand side, I'm going to have AB in the J. K cross I gives me J, so I'll have minus alpha L over 2 times the cosine of the angle theta in the J. And K cross J gives me minus I, so I'll have plus alpha L over 2 times the sine of the angle theta in the I. Okay, now let me pan down here a little bit. I can now pull off the I and J components, so if I pull off the I, I'll have AGX is going to equal alpha L over 2 times the sine of the angle theta. And if I pull off the J, I'll have that AGY is going to equal AB minus alpha L over 2 times the cosine of the angle theta. We can call these equation 6 and equation 7 respectively, and you now realize we have a system of 7 equations and 7 unknowns which we can solve using the steps to linear algebra. It might be a long process, but I know you guys got it. So I'll simply bid you adieu and the best of luck. Take care, everyone.